So this is one example on the finite element analysis. So if you see in the picture, there are different colors that are usually described in the software. So usually the more red color, the more red the picture becomes, it means that there will be more stress distribution or more concentrated load nearby that area. Okay, like it's here, example here, this is in for a space shuttle design, so for NASA. So you see that the red color means that there will be more stress distribution or more concentrated load. Okay, and this is using the usually the most software used are Nastran or ANSYS. I think more people using Nastran to describe this phenomenon. And we have discussed yesterday about this, how this could be solved by the finite element, by the if we know how the stress distributed, and the mechanics of materials will give you those fundamentals. So this is also last time we discussed about this. So we are going to start with the equilibrium, which means that we are going to start with some equations that usually we start with the sum of F equals 0, and then the sum of moment at the origin or at some point. Okay. These two will be our main equations. Okay. And of course, we could define the equilibrium using 3 dimensions. So in 3D system, so in 3D, we could have for each axis and also the moment. Okay. And there are some we call it external loads. Let me write here, maybe. Well, let me copy this one more time, and I will write in the new page. Let me write here. Okay. So the external loads, at least we have some loads that are described. First is the concentrated loads. This include the force or couples, the FL, and line loads. What is line load? Line loads mean the forces described by the distance. So this will be F over L. And then surface loads, what does that mean? It means that it depends on the area of the surface. So F divided by L squared. And then also body forces, which is volume. So F divided by L cubed. Of course, if we see this 4, we could argue that this is also similar to what we have in, for example, the pressure, force divided by F over A, right? It's kind of similar, but in mechanics of materials, we consider all these things is our loads. So it doesn't always necessarily to be exactly using the Newton. It could be Newton over millimeter squared. That is definition for a Pascal. So sometimes we tell the unit as a Pascal. Okay, so usually we use terms the dimension usually using the megapascal. or megapascal is Newton over millimeter squared. Okay, so we call pressure as a force. Of course, in physics, it's kind of different terms, but in our design for mechanical materials, we usually using this as our loads. Usually in material science, we use the MPa a lot, right? Usually for steel and for other material as well. And this is how it looks like. The descriptions. So concentrated force is exactly at one point, and then we have the couple, and then we have the line load, so it goes over this line, and then we have the surface load, like that. So only on this area, we call this is surface load, which means that the loads distributed among these surfaces. Okay. And this is also another distribution that you can see. So it is going all the way. And then I think in statics you learn how to simplify this by taking this in the middle, right? If you have this rectangular shape like this, the distributions, you see that this will be exactly at the half distance. We can simplify this as a concentrated force at the distance for this distribution loads, right? So we could say we can be newtons, and it could be the Pascal or megapascal. And another thing that is important is the support reactions. The support reactions that I mentioned before, it could be described as this. Okay. It could be roller support, so it could be like this or like this, the same. The effect the same. Or it can be cable or rod, like you have a thin line, usually if you see the drawing, or if you do the description of a line like that, and maybe having some angle like that. And if this cable around, it means that we could have some tension. We call this tension, right? And then we could have the pin support. Okay? The difference is the roller and the pin supports. So imagine that this roller, because it has rolling conditions, so it could move, at least we could move horizontally. So pin support, it is fixed on that point, so it's fixed on the vertical, fixed on the horizontal, so you cannot move. You cannot move. And then you have cantilever support. So you are maybe some member of the bar fixed on the wall, so it couldn't go anywhere, or maybe fixed on another bar. Okay, so it cannot go over there, it cannot go over there, and it cannot flip around. Okay, it cannot flip around. Okay, and then we have ball joint. Ball joint, it's fixed on all directions, but since it's a ball, it still can roll. Right? It can roll. I don't know if do you play with like a toys or maybe action figure? Usually it has a ball joint, but it can move the arm like that, right? Okay. And we have also the cantilever support, which it will be fixed, so it cannot move the translations, and it cannot rotate. It cannot rotate. We can have pin connections. So pin connections, we can move here, right? So we could describe the concentrated loads. So if there's some loads that is pushed through this bar, we could define this using two axial tension. Okay, we can have this y on and x. Okay? So if we would like to see the sum of the force, we could see y, all the y we could combine all together, and all the horizontal combine all together. Okay. And then we have also the rigid connections. It could be weld or bolted, so between these two members. And we have the vertical, horizontal, and then the moment, And so if you see that if there are two members like this, we could always separate them, and then actually, what we did here is for example, you see that this is going up. Actually, you can try and imagine this is going down. But if you do this, then this will be the other one. Should be the same. If the result is negative, like when you calculate, if any calculation the result is negative, it means that the directions is on the opposite way. Okay? In statics, remember. So it's okay if you are maybe assuming wrong direction at the beginning, but if you consistent all the calculations and you get the negative one, so it means that the direction is actually the opposite way. Okay, so that's okay. That's okay. But when you are practice along the way, you will know which one is going up, which one is going down, because you will be familiar with the condition. Okay, so there are some example for the support reaction and member connections. Okay, and this is how we see the internal resultant. Sometimes we need to do this to consider. So not only external forces, but we need to consider. So it means that this will be force and couples that are internal to the, let's say, body. Okay. So usually how we get the internal resultant is it's by cutting the member of the bodies. So we can cut in every member. So for example, since we know that this will be x, so maybe at certain point of x we slice, and then we can imagine some internal forces that is going around. Okay? And of course, the more you get maybe more complicated conditions, it means that you can do two observations. First is you have shape 1 and you have shape 2. Shape 1, we could get this and that, so we can make it into vertical and horizontal axis for the forces, and then you can get how the internal forces will be. Okay? And all these internal forces will be the same with this, okay, because this will be canceling each other. And of course, depends on the question, whether maybe asking what is this or what is that, or maybe if the member is strong enough to withhold these P forces, this also can be a question. Okay? And of course, another internal resultant. So another name for this one is the method of sections. I don't want you to memorize it, but this is what is called the method of sections. And then we could have this resultant if we consider 3-dimension shape. So we consider there will be related to the x-axis, y-axis, and z-axis. So each one of the axes, they have f and m. So f of x, and then we say perhaps the moment will be t of x, and then for z this will be phi z, and for the y is the my. And this described as m because if we see the shape, this will be certainly the shape that has the moment that is my. Okay. And this dx is another couples, phi z also another couples. Okay? But when we talk about m, it means that this is exactly the moment of this shape. Okay? So that is the conditions. So this is called the normal. Let me write here. This is the normal force or axial force. And this will be called the shear force, the phi. And then the moment that is on the axis, which we call the t, this is we call the torque or twisting moment. Actually, all of this rotation called moment, but they have special name. And the my and mz, this is the bending moment. Okay. Okay, that is some introduction and how to use at least the method to cut or slices the internal forces, and then to observe whether we can figure out how to determine axial forces. For example, let's say we have an example here. Let me start with the some constructions. Okay, we have all pin connected, and then it has some sign. So let's say sign of the name, maybe the restaurant, and then we know that it has the loads, 600 newtons. It hangs on the pin jointed planar truss. So this is the truss that is connected through the pin. Okay. So use method of joints to determine the internal axial forces F1 and F2. That is in CD. CD is here, and DE. D is here, respectively. Neglect the weight of truss member. So we ignore the weight of the truss. So the weight that we consider is only the 600 Newton. Okay. And then number B, use method of section to determine the axial force F5 in FG. FG is here. Okay. So let's start doing this. So perhaps we could start by start by taking this. Okay. So let's cut this off. So we have this is one, right? And this will be okay. So this is 2. Or maybe let me write this is just D. Okay. pinch jointed D, and we have, or maybe before that, since this is 600 Newton, and we have two cables, okay, on the 600 Newton, so this will be having this one, each one of them are 300 Newton and 300 Newton, right? So we could just divide by 2. So the cables from the sine are 300 Newton. So on the point, on the pin D, we are getting another 300 Newton here going down, right? Okay. And then what else? We have the length. We have the length. The length are, you see that this is another tips. Okay? If you have the length like this and you have some kind of triangle positions, you can use the ratio of the triangle to get the sine or cosine, or you can get the angle. Or perhaps I think better is to look at this triangle here. This is 0.9 and 1.2. So if you have 9, 12, the other one will be 3, 4, 5, right? Okay, you get it? So if we get this, let me write here. So we get the, this is 0, sorry. This is 0.9. This is 1.2. Okay, so this is, if you divide by 3, or so if you divide by 3, we could get that this will be, let me erase this, this will be 3, 4, and of course if this is 3 or 4, it should be 5 here. Okay, so what's the 3, 4, 5 used for? It used for to describe any forces that is not in horizontal or vertical. So you have the diagonal forces, and you can split this diagonal into horizontal and vertical, into x and y. Okay, I hope you get that. Okay, okay. All right. So from this D again, D, we have cable 1 and cable 2, which we could describe this as F1 and F2. And we have 3, 4, 5 as the ratio. So if you could have that, which means that if we have, this is F1, this is F1 cosine, right? This is F1 sine. If it's theta here, right? So start by taking the, since all the condition is only for now, we can only observe the axial forces. So we could start by taking this x equals 0 and then the Fy equals 0. Okay. Now let's start with the x. Okay. X, start by taking F2, and usually one standard to help is every time you see the force going to the left, we say it's negative. If force going to the right, it's positive. Okay. If you're going down, negative, going up, positive. Okay. Just to help for calculations. So let's start for x, or maybe let me write. Oh wait. Maybe just right here, right on the left, or maybe let me write later the y. So this will be negative F2, and then negative F1 cosine theta equals 0. what will is cosine theta is basically the 4/5, right? So if this is theta here, it's 4/5, right? Cosine. So we could write that the negative f2 negative 4/5 f1. I think we couldn't do anything left, so we could just put aside and we get through the another observation, which is from the vertical. So the vertical, we could get this is the directions, the f1 sine and then minus 300. Okay, now sine is 3/5, so 3/5 f1 equal to 300 Newton. So f1 is 300 multiplied by 5/3, which is 500 Newton. So because f1 is 500, so we could get this. So f2 is negative 4/5 f1. F1 is 500. So this will be negative 400 Newton. What does it mean? It means that since we assuming on the left, but it's negative, so the actual direction is to the right. But my suggestion is let it be, okay? Just keep this way, okay? Keep this way and then keep this negative, because we still have some other questions left, right? Or if you want to answer that the F1, let me write here, so the F1 is 500 Newton. Since it's positive, we call this a tension. And F2, we call 400 Newton, but it's a compression. Or you could simply write T or C, okay? Just to describe what's happening, okay? And then the second question is to calculate the F5 using the method of sections. So method of sections, 5 is on FG, right? Yeah, 5 is on FG. So we want to have this, but since our external load is here, so we need to have at least, we need to include this up until here with this. Okay, so we have here, so we cut all these wires, okay, or truss, so we write that part. Okay. So we are going to have, so we have the F here, we have the C, we have D, we have E, okay, and we have all conditions, and we could start here is 300 Newton, this is 300 Newton, and then since this is, we cut, so we have here is the F5 that we want to find, and on the F we have also 4, right? So this is going F4, and we have also C, or maybe let me write here, this is like that, and C is, we have another one here, right? That is the member 3, so force 3, and then yeah, that's all. And we can have, let me write here just to describe the length. So this is 0.9 meter, and then there is another one here, which is, this is B, and this is another 0.9. Okay, and this will be 1.2 meter, 1.2 meter. Okay. Okay, now we could take the this conditions. So we imagine that the sections were imaginary cut. Okay? We cut and we make a new free body diagram. Okay. There will be three unknowns, right? There will be three unknowns, which is the F3, F4, and F5. Okay. So what could be done to calculate? So this time we could have some options. Okay? Either we take this, okay, we could take the moment, for example, because we want to know the F5, then how about we take, if we take the moment here, okay, we take the moment here. So if we take the moment on D, every aspect, like for example here, F4, as we go around that, right? And here we could describe F3 as with sine and cosine, we can have that. Using the same triangle with before, we could have that. But we have F4 and F3, which we don't know, right? So we need to find which reference that we can take so that we can focus on finding the F5. The reference that should be done, and we could just write one equation and you can get the answer, is by using B. Okay? If we take B as our reference, so you see that here, if we take B, the point B here, every aspect of all the forces, we could see and we could done, for example, the 300, we could make it like that, using the angle and ratio. So we could make going there, and this is also going there, using something that the light over here. And this one also can take the moment over there, using this line, the 0.0. So you need to justify the line first, and you don't need the F4 and F3. You don't need the F4 and F3. Okay, so by taking reference on B, we are going to have sigma moment of B. And usually when we write the moment, usually we write on the left side rotations, that this rotation is positive. So every time we see this rotation, we see positive. If we see the opposite rotations, it means that it will be negative in our equation. So we can write now. So first we start from the E. We can start from the E. B is here. Okay, so 300 going here, so only 1.2. So 300 Newton multiplied with 1.2 meter. Okay, and rotation is the same, so positive. And then another one here, it will be this much, 2.4, right? And it's still positive, so plus 300 Newton, 2.4 meter. Okay, and then lastly, F5, B is there, so you get this length, which is 1.8, and again it's still positive. .8 meter, and it's equal to 0. Okay, because we're still in the statics. Okay, so it's 0. And then we calculate. So 3.6 by 3. 3.63 108. So this will be 300. This will be 3.6 meter negative. So this will be F1 divided by 1.8 meter. Oh, this is cancelled, it's 2, so F5 is 600 Newton negative, right? Or we could write F5 is 600 Newton and write C as a compression. So if we want to review what is happening, so F1 is becoming the tension, okay, F1 is tension, and F2 and F5 is compression. And I think based on the number, okay, the number 500, 400, 600, compared with the weight, the external load set is 600, I think the solution are still sounds makes sense, right? So from 600, it's divided through some 500, 400 for F1 and F2 for this one, and then 600 on this 5, because this is going to be, if you imagine, like remember the diving board like we talked yesterday, the more distance it has, the moment is bigger, or the field, the point on the farther away is much more higher, right? So this one is holding really high loads, right, in this member, right, because it has more distance and then it has 600. So it is makes sense if this F5 is also 600. Okay? And of course, we simplify the question that the member no weight, right? No weight on the member. So we simplify. So that's how we did it. So I think this is still the statics, right? How to assume the condition and so on and so forth, right? And maybe for your exercise, I think we could start this, okay, this one. If you want to take picture, you can take picture this. I will also put into the Moodle later. Okay. So this and this. So we have two exercise that I think the exercise will be done next Tuesday.